Hello everyone. It's my pleasure to introduce our work about community detection and search in heterogeneous information networks. I am the first author of this paper. This is a joint work conducted by the Hong Kong University of Science and Technology and Shenzhen Institute of Computing Sciences. My presentation contains 5 main parts. In the first part, I will introduce the background and our motivation. Then I will describe the target problems in this work, which are followed by our solutions. Finally, I will show the experimental results and conclude our work. First, let me introduce the background. Heterogeneous information networks, or HIN for short, is a graph who has different types of nodes and edges. For example, in this bibliographical network, there are 3 types of nodes: A for author, P for paper, and V for venue. Compared to homogeneous networks, HIN stores richer information and semantics for entities and links. Community detection and community search are common tasks in graph analysis. However, in HINs, they are not well handled by existing models. For example, the connectivity between different types of nodes can be heterogeneous. In the BIP network, we may want to find a community where each author publishes more than 2 papers and each paper has more than 3 authors. However, no existing models can deal with such constraints. So we need a community model for HINs, which deals with connectivity requirements and can model real-world communities. To do so, we first define the community schema. A schema S is a set of triplets. Each triplet specifies a connection requirement between 2 types of nodes. For example, triplet AP2 means each author node should connect to at least 2 paper nodes. Then we define a relational community R as a connected graph, where every vertex satisfies all constraints in the schema S. In this figure, R is a relational community satisfying the schema S. Now we formally define the problem of detecting and searching relational communities. Specifically, RCD is to find all maximal relational communities in G, and MRCS is to find the minimum relational community containing the query node Q. We also prove that although RCD can be solved in polynomial time, MRCS is NP hard to approximate. So we will focus on approximation solutions for MRCS. For RCD, our solution is to iteratively remove nodes that violate any constraints in S. And we use message passing between neighboring nodes to avoid redundant scans. In this example, in the first step, our algorithm scans the whole graph once and removes nodes that violate the schema. Then for each removed node, we send messages to its neighbors. These neighbors are then tested and removed if they violate the schema. The algorithm repeats this process until no more nodes are removed. When it ends, each connected component in the graph is a relational community satisfying the schema. To further improve the efficiency, we devise a count index to track the number of neighbors of each node in different labels. We show that if the schema S is not large, the time complexity of this algorithm is linear to the graph size. For the MRCS problem, we propose 2 approximation methods, greedy and local search. In the greedy solution, we first find the maximal community containing Q, which is denoted by RmaxQ. Then for each node in the community, we try to remove it and check whether a smaller community R' containing Q still exists. For all R' found in step 2, we keep the smallest one to minimize the community size. Finally, we repeat step 2 and 3 until no more nodes can be removed. This algorithm has time complexity cubic to the number of nodes in RMaxQ, which is not efficient. So we design a local search approach to improve the efficiency. The intuition is that while shrinking a large community is costly, a small community may exist near Q. So searching a local area may find a feasible answer quickly. This approach contains 4 steps. We start with the vertex set Q, which contains only the query node, and the candidate set C, containing all neighbors of Q. Then we iteratively add candidates U from C to Q, while expanding C with U's neighbors. This step stops until a community is found in the induced graph, GQ. Finally, we use greedy to further reduce the community size. For this method, we propose several optimizations. When selecting candidates, we set a node priority to balance the width and depth of the searching space. Here, the width is the number of connections between candidate U and Q, and the depth is the distance between U and the query node Q. We also use candidate pruning to remove candidates in advance, so that Q is kept small. For example, V4 is a candidate which satisfies the schema. However, if we know that V5 violates the schema, we also know that V4 cannot be in any community. So using the message passing approach, we can remove V5 and V4 from the candidates. This can effectively reduce the searching space. Finally, we propose the round index to help check whether a community is already found. In brief, for each node, we set a round number, indicating how many passes are needed for the naive scanning approach to remove it. Then nodes in a community will all have infinite round numbers. We devise efficient algorithms to create and update this index, so it can both accelerate the local search and handle dynamic graphs. In the experiments, we use 4 real-world graphs to test our methods. To show the effectiveness of the proposed community model, we evaluate it on the DIP dataset. This graph contains thousands of pertains, and each known complex is a ground truth community. We use schema extracted from 10 known communities and compare our model to the degree-based community model. We use a common measure from existing works, which maximizes a partial mapping F from detected communities to the ground truth. It is shown that our model outperforms the degree-based model in both the mapping size and the F1 score. For the efficiency of RCD, we use synthetic schema to evaluate the message passing method against the naive method on 3 large datasets. It can be seen that count index is time and space efficient, and message passing outperforms naive in all datasets. For the efficiency for MRCS, we also use synthetic schema and query nodes. We compare greedy local search with round index, and the naive method on 3 large datasets. It can be seen that local search with round index has the best performance, and the index size is low compared to the original graph size. So this is the conclusion part. We propose a relational community model that can specify connectivity requirements between different types of nodes. While detecting relational communities is easy, searching a minimum one is NP hard and even hard to approximate. We propose efficient algorithms for detecting and searching relational communities. The searching algorithm can handle dynamic graphs efficiently by its nature. We conduct experiments on both synthetic and real-world datasets. The experimental results illustrate the high effectiveness and efficiency of our proposed methods. That's all. Thank you.